two things that we're going to make use of. If A is positive, definite, and symmetric, then the determinant of A is the product of the characteristic groups. And the trace of A is the sum of the characteristic groups. These are things that you had to do proofs for when you took linear algebra in prehistoric times. If A is symmetric and positive definite, then the determinant of A is the product of the characteristic groups.
Which is the eigenvalues, right?
Yeah, characteristic groups and eigenvalues are the same.
The traces you get from
The sum of the roots. Suppose that we have a random variable that we'll call xi, and all the xi are independently, identically distributed. So I'm telling you that the xi are random variables identically, independently distributed. And x is the random vector that looks like that. What's the algebraic representation of that density? What's the density function for that multivariate normal? Remember? What's the density function for one of them? You know what the univariate normal is? How we write it down? Algebraically. Okay, remember that? So then the joint density of x must be, let's put this back together. Okay, so that's the joint density for the random vector x. So if the individual x's, the xi that make up that random vector are I, yeah, is that 2 pi to the n? Yes, 2 pi to the n over 2. It's 1 over 2 pi n over 2 to the power. And then the determinant of omega raised to the 1/2. And then e, the exponential operator, e to the minus, minus sign after n over 2. What does omega look like? What are the elements of omega? Given that the xi are IID, normal to mean unit and variance sigma squared. What does omega look like? Yeah, given what we have here, what's the dimension of omega? The dimension of big omega is n by n, is the dimension of big omega. It's a matrix. Okay, so big omega is n by n. And so what's in it? What's the covariance between x1 and x2? If these random variables are independently, identically distributed? 0. What's the variance of x1, according to what's up there? Right, and what's the variance of xn? Sigma squared, right? Can we say anything about the definiteness of omega? What kind of definiteness did we talk about a few minutes ago? What flavors did definiteness come in? We can say that big omega must be, so you told me before you said it was positive. Definite. But Lacey said he thinks it could be semi-definite. Jeff Morrow. So what do you think? Think big omega could be positive semi-definite? Okay, what would be the implication if big omega was positive semi-definite? What's the implication? Semi-definite means that if we used omega to make quadratic forms, it would be possible to find an x such that x transpose omega x was 0. But what's the implication for the random variables if omega is semi-definite? It means that one of them is not a random variable.
Yeah.
One of them is always the same. The only way out of this diagonal matrix to get semi-definiteness is if one of the sigma squareds is 0, in which case the multivariate distribution is degenerate because one of the x's always takes the same value, has no variance. As a quadratic form, does omega, when you plot omega as a quadratic form, does that quadratic form look like a circle or an ellipse? Given what we've done so far, we said that the xi are IID. It's like a circle. Right? If the xi were not IID, if instead they were multivariate normal where the terms on the main diagonal were all different, we'd get an ellipse. But the orientation would be along one of the axes. Suppose that the off diagonals were not 0. Then what we're doing is we're saying the x's have a non-zero covariance, and therefore the shape of the error distribution, or the shape of the random variables distribution, is elliptical and turned off the principal axis a little bit. So there's a geometric interpretation of this joint density. So you should be thinking that if the univariate density looks like that, then and the variances are all the same, and the off diagonals are all zeros, then you can just rotate that two-dimensional picture. You can just spin it on the vertical axis, and you get the bivariate density. Or if you have good imagination, you can do it in many dimensions. Okay, but in two dimensions, you just spin it on the vertical axis, and you get the three-dimensional density. Okay. And then if you look down on it from above, it looks like you're looking down on a mountain. The contour map, you get concentric rings.